Hello everyone, welcome to my group theory lecture. In this lecture, we continue to study Lagrange's theorem. So this is going to be the last part of my lecture on Lagrange's theorem. So now, like I said last time, we are ready to, uh, talk about our main topic, Lagrange's theorem. Okay, so before we do that, we proved this lemma, right? Last time, right? So, again, G is a group and H is a subgroup, and R, is an equivalence relation. The equivalence relation on G given by the following definition, right? Where in this case, for any uh, element A in G, the equivalence class of A is same as the right coset HA. So that's what we proved the last time. What's the significance of this? Okay, very important. So whenever you have it, group G with a subgroup H, you can always, define this equivalence relation, right? And this equivalence relation partitions, okay, this equivalence relation partitions the group into cosets, into right cosets, okay, by the, this theorem, okay, by this theorem here. So that is going to be the starting point of the Lagrange's theorem. So what is the Lagrange's theorem? So here's the statement. If G is a finite group and H is a subgroup of G, then the order, remember order, right? The order, the number of elements of a group is called the order of the group. So the order of H always divides the order of G. Okay, this is actually very important. So in this case, the order of H divides the order of G. Okay, this Lagrange's theorem is due to, were named after uh, the great French Italian, uh, mathematician, physicist, and also astronomer. So he did a lot of it. You know the great works in those three the branches of science. The mathematics, physics, astronomy. Joseph, Louis, Joseph Louis Lagrange. Actually, that's the French pronunciation. Uh, for his name, Lagrange. But the it, I usually try to pronounce like the people's names, the following like their the respective the languages. However, in this case, if I do that mixed with English, it sounded really funny. So I was sticking to English pronunciation Lagrange, but it's supposed to be Lagrange. Okay, so Joseph de Louis Lagrange. Okay, Lagrange. But anyway, it's not important. So, what's the statement? If G is a finite group, and H is a subgroup of G, then the order of H divides the order of G. Okay, so that's the statement. Let's prove this. So earlier I mentioned that because of the lemma, the preceding lemma, we know that the right cosets, okay, the right cosets of H in G maybe I can do this. So this is G. Okay, group G. So we can partition. Okay, we can partition this G into coset. So one of them has to be, since identity, okay, identity is an element of G. So one of actually cosets would be the group subgroup itself H, right? So that's the right coset HE. It's like looks like what the chemical, the symbol for helium, but that equals H, okay, so here H, A, HB, HC, and so on and so forth, right? So, partition HD, HE. Oh no, not the, it's not. Sorry, it's not HE. And so on and so forth. Okay, and so on and so forth. Right. Right. So the the bottom line is right. Due to the preceding lemma, we know that group G with given like a subgroup H, right? The equivalence relation, defined by the uh, the subgroup H, this particular the equivalence relation, right? Partitions, right? So uh, the, the group, okay, partitions the group, and in this case we know that the equivalence classes, right? So the equivalence classes are same as right cosets. So cosets actually form the partition, right? Cosets form the partition of a partition. Okay, the cosets form a partition of this group G. Okay, so now we are ready to prove the Lagrange's theorem. Okay, so by the preceding lemma, we have what is it? G equals H sub A1 union H sub A2 union dot union H sub AK and we have only finitely many the right cosets because obviously G is a the finite group, right? So there are only finitely many elements. And the right cosets, since these are equivalence classes, they are pairwise disjoint, right? Pairwise disjoint or mutually disjoint. So we also know that H sub I intersection H sub A, HA sub J, HA sub Y intersection HA sub J is empty if I and j are different, here both I and j run from 1 through k, right? 1 through k. Okay. So obviously, the order of G is the order of each coset, right? Each coset. So by adding the order of each coset, we can get the order of G, right? Uh, yeah, I was actually a little ahead of myself, but yeah, here. So in this case, due to right, so we're gonna get to that again. Yeah, I was like a little bit ahead of myself, but due to okay, so due to the cancellation law, okay, so we have a cancellation law that holds for groups. The order of h, okay, right? The order of h the same as the order of a h sub I. For all I running from 1 all the way through k. So I mentioned earlier the order of h here in this case can be obtained by adding, okay, adding the orders of those cosets. Okay, so that's sum I equals 1 through k, the order of h a sub I. Okay, and since the order of each coset is same as h, the same as this. And since we are adding the order of h, right? So k copies of them. So this equals k times h. No, actually the order of h, right? What does that mean? That means, so the order of g is an integer multiple, of the order of h. In other words, the order of h divides the order of g. This divides the order of g. So this completes the proof. Okay, we just proved the Lagrange's theorem, right? Uh, we actually talked about this, at some point, earlier in one of my, the earlier lectures. But as a reminder, what it means is, so say, uh, so if you write, we talked about this when I was proving that, the G is a group, right? G is a group, and the H is a finite subgroup of G. No, I mean finite subset of G, right? In that case, the all you have to do to show that, right? Let me rephrase that. So the G is a group and H is a finite subset. If this finite subset is closed under the operation of G, H becomes the subgroup. So you don't have to check about anything else. All you have to do. This is true only for a finite subset of a group G. So if this finite subset is closed under the operation of the group, it is a subgroup. So we talked about that theorem, and when we proved it, we use actually this cancellation law. But as a reminder, okay, right? So He is finite. So A, we can write it as A1 dot 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 A sub n. No, I mean this has nothing to do with this Lagrange's theorem. Okay, I mean I'm just explaining what we talked about earlier, right? The theorem. So here actually, A sub y, these are different ones. Okay, these are different ones. So in that case, if you multiply, so here, the pick an element A in H, right? And we consider the following, the coset. Okay, so actually coset notation I used earlier. So A1, that's going to be A dot 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 A sub n A, right? In that case, we know that A I times A equals A J A, right? That if and only if AI equals AJ, because the groups satisfy cancellation law, right? This A, where at that time, here in this case, it doesn't matter because H is already subgroup. So, the A inverse also exists in H. But when we proved that theorem, the argument is that A is also, the element of G. So, so there is A inverse, right? There is A inverse. So really, I mean, inverse belongs to H or, the A, it doesn't matter. But anyway, using that inverse, we can get this one. So what this shows us is that, in fact, exactly HA, the right coset has exactly same number of elements as H, right? So that's a reminder. Okay, maybe, I'm gonna just I'm gonna put a box around it. Okay. So that's Lagrange's theorem. If G is finite, the number of right cosets of H in G, okay, there are finitely many right cosets, right? Namely, well, you know that the number of earlier, let me get back to this, right? So that's it. We have exactly k number of, in this particular, like, the proof setting, there are like a k number of the right cosets, right? That can be given by, because the order of G equals k times the order of H. So k is given by the order of G divided by order of H, and here this guy is that's the number of right cosets. Okay, the number of right cosets. So we have this, right? That's the number of right cosets. Now this is called the index of H, index of H, the index of H in G, right? That's the name, the index of H in G, and it's denoted by this notation or that, okay? But I prefer to use this first notation, so that's what I'm going to use from here on. Okay, so we use this notation for the index of H in G. Uh, the converse of Lagrange's theorem need not be true, by the way. Okay, for example, the alternating group of degree 4, I'm supposed to say degree 4 here, that's missing again. Okay, so I'll fix that after this lecture. So A4 has the following members, okay, the following elements. There are, what is that, we have nice like a formula for the order of alternating group, right? In fact, the uh, the order of a symmetric group, like S sub n is what? N factorial, right? N factorial. And there are exactly the same number of odd permutations and even permutations. And, alternating groups are what? Formed by, the collection of all even permutations. I'm just trying to, recap like what we studied, some time ago, right? So, so the order is going to be n factorial divided by 2. So in this case, 12 factorial divided by 2, right? No, I'm sorry. Uh, 4. So 4 factorial. I'm sorry about that. So S4 This alternating group of degree 4, A4 is a subgroup of the symmetric group S4. So S4 has, the order 4 factorial. So this guy has a 4 factorial divided by 2. And so that's going to be 12, okay? 4 factorial divided by 2, that's going to be 12. So there are 12 of them, right? 12 members. Now this alternating group does not have a subgroup, okay? Does not have a subgroup of order 6, even though, the 6 divides 12. So this is a counter example of the converse of Lagrange's theorem, okay? Right. So, there is a number, okay? So, that divides the order of G, but that doesn't mean that, the group is going to have a subgroup with that, the order, okay? Right. So this counter example shows you that. Okay, so next theorem, a group G of a prime order. Okay, the group G of a prime order is secret. Okay, this is very important and useful, right? Okay, theorem. All right, so this can be actually proved using Lagrange's theorem. So we're gonna get back to my notepad. Theorem. A group G of a prime order. So the order is a prime number. Is always secret, okay? Always a secret group. Secret group, you remember that, right? A group generated by only a single element, right? Okay, secret group. So we prove this. Let's let the order of G be P, a prime number, okay? A prime number. A prime in short. Also let HB a subgroup of G. Then by Lagrange's theorem, we know that the order of H must divide the order of G. But the order of G is a prime number, right? So the order of H, so we have either one of the following two cases. Okay, so either the order of H equals 1, or the order of H equals P itself. So we pick, if we pick an element A, okay, which is not the identity element in G, right? In G, the cyclic subgroup, generated by A as a subgroup, okay, is a subgroup of G, but because of this, okay, right, since this is not identity, it must be, okay, it must be the same as the group G itself, right? So this completes the proof. That's pretty neat, right? That's pretty neat. Okay, so here's a definition. If G is finite, then the order of an element, which is not the identity, right, is denoted by, this notation or this notation. Actually, I'm going to stick to this notation here. The absolute value. It's not absolute value, but yeah, the first notation. Okay, to be consistent with the notations the notation I have been using, it's the least positive. Okay, so that's the definition of the order of an element. That is the least positive integer n such that a sub n, equals identity. Okay, that's the definition. So let me explain a little bit about this, okay? So, let G be a group, finite group, G be a finite group and A be an element of G which is not the identity, then H, which is the cyclic subgroup generated by A, okay? Right, so G is a finite group. So of course, this is cyclic, the subgroup H, right, generated by, the A is also finite. okay, is also finite. So, we know that, so a to the power m is going to be eventually, right? Eventually, m, eventually it is the identity, right? For some integer, positive integer, n. But there are, infinitely many, there's such integers, okay, which makes, a to the power m equals c, because it keeps repeating. There are, this is a cyclic group, okay, so it keeps repeating. Uh, uh, so, there are infinitely many such exponents that make a to the power m equals e. Okay, so among those, the smallest positive integer that satisfy, this property, this equation is called, the order. Okay, so order of element A. Maybe actually, I mention a little more. H is finite, right? H is finite, so it's it's clear, but so it's E. It's generated by that's secret subgroup, right? Generated by A. So A squared, A cubed, and so on and so forth, all the way to so A sub n. Okay, so A sub n, right? But then what is that? A sub n plus 1 is going to be, oh, no, it's I meant A sub n minus 1. Okay, so A sub n minus 1, right? So A sub n is going to be, in this case, what? Goes back to E. That's A sub n plus 1, n plus 2, n plus 3, and so on and so forth. And then, like what? A sub 2n is going to be E again. 3n, 4n, and so on and so forth, right? So there are infinitely many, the positive integers that satisfy this equation. But among those, the least one in this particular case, right, setting, that's n. So, here, the order, in this case, we say the order of A equals n. Okay, so that's what I meant. Okay, corollary, if G is finite and, an element A, right, A is an element of G, which is not the identity. So in that case, the order of the order of the cyclic subgroup generated by A divides G. I mean, there's nothing to you know, mention any further, right, about this. This is simply what, the Lagrange's theorem, because, for any, right, element of G, the cyclic, which is not the identity, by the way, the cyclic subgroup generated by A is a subgroup. So obviously, the order has to divide, the order of G. Okay, so that's going to be our last theorem. If G is a finite group of order n, then A to the power n equals identity. Okay, right? So for any element of G, if we take the raise that element by the exponent n, which is the order of the group, that has to be the identity. Proof is easy. Let's go ahead and do that. Okay. If G is a finite group, finite group of order n, then A to the power n equals the identity. Okay, for all or for any, doesn't matter in this case, right? A in the group G. Okay, so let's prove this. Let A be an element of G, which is not the identity, and also let the order, okay, the order of the cyclic subgroup generated by A, right? Let's call it K. Then by Lagrange's theorem, K divides N. Okay, K divides N. So that means N is a constant multiple, an integer multiple of, a positive integer multiple of K. So this N can be written as K times L for some positive integer L. Now, a to the power n equals a to the power k times L, and that can be written as a to the power k to the power L. So k is the the order of the cyclic subgroup generated by A, which is also same as the order of A, right? Order of A, by definition, right? So anyway, so A to the K is what? Identity. Okay, A to the K is identity. So this equals the identity to the power L, and that equals E. So this completes the proof. Okay, folks, this is it. More details of my discussion, right, in this lecture can be found in my lecture note at the following address. As usual, this is a hyperlink. So all you have to do is to click on this address to get to the lecture note. And if you are interested in visiting my main blogger site, where you can also find the many other lecture notes of mine in different subjects. All you have to do is to click on this word blogger, which is also hyperlinked. And also, problem set 4 for this, the Lagrange's theorem is available at the following address. Okay, and my Google site, pretty complicated, right? But you don't have to type this to get there. It is hyperlinked, so all you have to do is to click on this address to get there. Thank you very much for listening and watching my lecture. Bye-bye.